So far in this course we have hello everyone. So far in this course we have learnt about different methods to estimate design seismic load. However, the process needs to account for some eccentricity, as it will be more clear as we go through today's and the next class. However, the process needs to include some eccentricity in case of torsionally irregular buildings. So, first of all, in this class we will try to understand what are torsionally irregular buildings. We will also understand it through an example problem depicting determination of center of mass and center of resistance. And further we will look into how to account for such torsional irregularity. So, when your center of mass and center of resistance are located far apart from each other, we call such buildings to be torsionally irregular. Let us understand why. Because the inertial force, as we are already aware that in case of any structure subjected to dynamic excitation, we have an inertial force, we also have stiffness force or the force of resistance. Okay. The inertial force is applied at the center of mass and the resistance force is applied at the center of resistance, and therefore if these two forces if center of mass and center of resistance are located far apart, these two forces will generate a twisting moment, and this twisting moment will be a moment about the vertical axis. How? Let us say that this is the building plan and we have the center of mass and center of resistance at different points. The inertial force is applied at the center of mass, the stiffness force is applied at the center of resistance. These two forces will lead to a twisting moment about the vertical axis, and the building will tend to develop rotation about the center of resistance. The center of resistance is very similar to the shear center that you would have studied in case of structural mechanics or solid mechanics. So, essentially for any given building, the center of mass and center of resistance will never really coincide unless until it is a 100% symmetric building. However, for a small deviation, the building may not develop significant torsion, but if this deviation between center of mass and center of resistance is large, then in that case we need to account for the torsion. So, let us try to find out the center of mass and center of resistance. When you are trying to find the center of mass, most of the floor mass is contributed by slabs and beams. For accurate calculation, we need to also consider the mass of columns, shear walls and infill walls. But when it comes to center of resistance, since the resistance in any building is generated by lateral load resisting systems, that is columns and shear walls mostly. So, in this case the center of resistance will be determined based on columns and shear walls only. We will see this through an example problem. So, let us say that we have a building for which the floor plan is given over here. This is a reinforced concrete building. We have the slabs which are 125 millimeters thick throughout, and these slabs are monolithically cast with beams, and all the beams have cross section of 250 millimeters by 350 millimeter, and each of these columns have cross sectional dimension of 300 mm by 600 mm. Okay. However, the orientation of columns are different. Some of the columns like C1, C3, C6 and C7 are oriented in one direction, while the other columns C2, C4, C5 and C8 are oriented in the other direction. However, their cross sectional dimensions are the same. The story height is 4 meters. Now, our job is to find the center of mass and center of resistance for this building floor. We shall assume that the grade of concrete is M25 and the density of reinforced concrete is 2500 kg per meter cube. We will ignore the presence of infill walls in the building. Okay. You can obviously, so you can consider the presence of infill walls. That is not a very difficult thing to do. We will make a remark for that. So, let us first start with determination of center of mass. Okay, so as discussed earlier, slabs and beams contribute the most to the total floor mass. However, for accurate estimation of center of mass, in this example problem, we have considered slabs, beams and columns. So, in estimation of center of mass, our first task is to list down the individual center of mass of different components. So, in case of slab S1, in this case, the slab S1 has a center of mass which is located at, and also after listing the center of mass of the individual components, we list down the mass of individual components. Okay. So, in this figure it is clear that we have considered the origin at this point and x and y axis as depicted in the figure. So, the slab S1 has the center of mass located at x equals 2.5 meters and y equals 7.5 meters. So, which is mentioned over here. For slab S2, the center of mass is located at x equals 7.5 meter and y equals 7.5 meters as well, which is written over here. I will take a sample beam, let us say beam B1, whose center of mass is located at this point, which is x equals 2.5 meter and y equals 10 meters. Okay. Similarly, let us say for column C1, which is located at this point, the center of mass is x equals 0 and y equals 10 meters as shown over here. So, we have listed down the coordinates for center of mass of individual components as xcm and ycm. We have now estimated or calculated the mass of various components. Let us say for slab S1, we have considered it as 0.125 into 5 into 5 into 2500. Why? Because the slab has a thickness of 125 millimeters or 0.125 meters. The plan dimensions are 5 meter in each direction and the density of reinforced concrete is given as 2500 kg per meter cube. So, this multiplied, so this product gives us the total mass of slab S1 as 7812.5 kilograms. And similarly for other components as well, let us see for one beam, where for beam B1, the length of the beam B1 is 5 meters. The cross sectional dimension is 250 millimeters by 350 millimeters. So, 0.25 into 0.35 into 5 into 2500 will give us 1093.75 kilograms of mass. Okay. Let us see for one column, let us say for column C1, we have the cross sectional dimension of 0.3 meters by 0.6 meters, the height of story is given as 4 meters and the density of concrete is 2500 kilograms per meter cube. So, this gives us that the mass of column will be 1800 kilograms. Now, in order to find the center of mass for the plan for the building floor, what we need to find out the product of mass and the x coordinate of the center of mass for respective components. We also need to find the product of mass with the y coordinate of the center of mass of respective components. Once we have these products determined, we will use expressions which is given over here to find the center of mass coordinates. So, the x coordinate of the center of mass for the entire building floor will be given by the sum of m times of xcm for different components divided by the sum of the mass. So, here the sum of the product of m and xcm is listed over here, and the total mass of the building floor is 48,775 kilograms. So, upon dividing we get the x coordinate of center of mass as 5.75 meters. Similarly, it is easy for us to obtain the y coordinate of the center of mass using this expression. Again we get a value of 5.75 meters. It is evident that though the building is not symmetric, but the presence of 4 columns oriented along one direction and the presence of 4 columns oriented along the other direction makes sure that the center of mass is located at the same distance along x and along y. So, the center of mass is located somewhere over here and has the coordinate as 5.75 meters in x as well as 5.75 meters in y. Once we have the center of mass, दिख नहीं रहा है इस पे स्क्रीन पे, हाँ उसके पहले कुछ आया था राइट बॉटम पे, कुछ लिखा हुआ ब्लू कलर के बार में,
कोई मैसेज टाइप का था।
हाँ कुछ मैसेज टाइप का, वो मेरे से कवर हो गया होगा वहाँ पे,
हाँ वो
है ना।
ठीक है, रेडी।
हाँ, once we are able to calculate the center of mass, let us try to calculate the center of resistance for this given building floor. So, while calculating the center of resistance, we know that the resistance or the stiffness comes from lateral load resisting elements, which include columns and shear walls. In our case, there are no shear walls, so we will be considering only the columns. So, we have listed this table for all the columns. So, in the table we will mention the coordinates for the center of resistance of different members. So, for any given member, the center of resistance will be located at its center of mass. Okay, so that's why. So, in order to have our center of resistance of individual elements located at their respective center of mass, we have divided these slabs into 3 components. If we had not divided, then in that case, okay, so the center of resistance of each of the column will be located at its center of mass. So, for example, for column C1, the center of resistance is located at x equals 0 and y equals 10 meters. So, at this point. Similarly, for column C6, let us say the center of resistance is located at x equals 5 and at x equals 10 meters and y equals 5 meters. Okay, and similarly it has been obtained for different columns and that is listed over here, and then we find out what would be the stiffness along x direction and the stiffness along y. So, when you are trying to find the stiffness along x direction, that is kx, you will use the expression k equals 12 EI by h cube. But when you are trying to find the stiffness along x, so when you are trying to find the stiffness, you will use the expression 12 EI by h cube, but you need to be careful when you are calculating the stiffness along x direction kx, you need to use Iyy when you are using the second moment of area. Why? Because if you are trying to find the stiffness along x direction, you need to consider bending about y direction. All right. So that's why kx will be given as 12 e times of Iyy divided by h cube, and that we have calculated it over here. We have assumed the modulus of elasticity of concrete to be given as 5000 root FCK. We have assumed the grade of concrete as 25 megapascal. For column, the second moment of area will be given as BD cube by 12. So, for column C1 we have shown the calculation. So, for column C1, when you are calculating the stiffness along x, you are considering the second moment of area about y, and therefore, the second moment of area about y will be given as 300 multiplied with 600 cubed divided by 12, and then the height of the column will be 4 meters. So, that's how we have substituted these terms to find the stiffness of column C1 along x direction as 25,312.5 kilonewton per meter. When you are finding the stiffness along y, then you need to use the second moment of area calculated about x axis. Okay. So, in this case you are able to find that the stiffness of column C1 along y direction is 6328.125 kilonewton per meter. Now, this is intuitive because C1 has a larger dimension along x axis, therefore, it will have a larger stiffness along x axis. So, it is intuitive and justified as well. Now, once we have found out the stiffness along x and the stiffness along y for different columns, we have listed over here. We have shown the calculation for only one of the columns C1, rest has been done in computer program Excel, and then after finding out these stiffnesses, we have listed them in this table. And after finding the stiffness along x and y, that is kx and ky, we will multiply kx with ycr and ky with xcr, and it will be more clear why we are doing that. When you are trying to find the x coordinate of the center of resistance, you divide the sum of product of ky with xcr divided by the sum of all the stiffnesses along y. Okay. Why? Because you are trying to find the x coordinate of center of resistance. If you are trying to find the x coordinate of center of resistance, the bending is about y axis, and that is why you are taking, when you are trying to find the center of when you are trying to find the x coordinate of the center of resistance, then in that case you need to take ky. You should be careful when you are trying to find the ycr or the y coordinate of the center of resistance, you are taking kx over here. So, you take these products appropriately, list them out for different members, take the sum and do the necessary calculation. In this case, we have done the necessary calculations. You can pause the video lecture and try to see if these calculations make sense to you. We have found the values of x and y coordinates of center of resistance as 5.25 meters and 6 meters respectively. So now, as we have earlier found the center of mass at 5.75 meters in either direction, the center of resistance is located at 5.25 meter and 6 meters along x and y. We find that the center of mass and center of resistance are not located at the same point, and therefore this building will undergo some torsion. In the next class, we will consider how to, in the next class we will discuss how do we consider this how do we consider this torsional irregularity in the building using eccentricity. Thank you.